Okay, starting a new recording then for lecture 4. So time varying predictors, other people call these time varying covariates, TVCs. I don't care what you call it. These are variables that you're thinking of conceptually as predictors, but are also measured at each occasion. That's the big picture here. So we'll start with what not to do, and then flavors of what you can do instead. So univariate MLM strategies are acceptable to some extent if you are dealing with models of fluctuation. They are likely not going to be acceptable if you're dealing with change. And I'll describe why that is as we go through this. The alternative is a multivariate strategy in which we let the model partition the variability into random intercept versus residual the same way we do the outcome. So that's the eventual place where this will end up with. Okay, so the joy of time-varying predictors. So even if you end up with a model of change, once you've accounted for whatever pattern of mean change there is, then we're dealing with a model residuals that are irrespective of time. Basically, at this point, the E's are agnostic as to what time it is, because all of the information about time has already been put in the model. So whether you have a Y that just fluctuates or a Y that changes, if you have the right model for time in, it will look conceptually like this. So I'm going to show you a bunch of pictures in this lecture. None of them have time on the x-axis. They're going to have some other variable on the x-axis instead, because time is irrelevant after you control for it via fixed and random effects as needed. So in terms of like a modeling process, step 1 is to get the time part right. Fixed and random effects, whatever change, whatever residual covariances, then we call that like an unconditional model for time. Step 2, usually for me, would be time invariant predictors, person things that would moderate the growth curve for different kinds of people. This would be like step 3, stuff that varies over time. The idea of why are you off your line today? That variability, things that are time specific, variability that is time specific can only be explained by predictors that are time specific as well. Why this is complicated is that the same exact concerns that we had for why we need a multi-level model for a longitudinal outcome in the first place operate if we have a multi-level predictor. Same exact things. Most predictors are going to have some degree of within-person variation. That's the whole point of collecting them. But they're also going to have the between part. And we have to have a way in the model to isolate these two different levels of variability and their corresponding relationships with the other outcomes. So this set of examples is going to be fluctuating types of data. Change is coming next, but not until after spring break. So the idea is that any time varying predictor is almost always going to be two variables inside one. That's the key idea. So if I think about measuring daily stress as some kind of outcome or some kind of predictor of something else, stress is supposed to be bad for you, we can all agree that some days are worse than others, right? Maybe not today, maybe not tomorrow, but some days. So if you think about the idea of your usual levels of stress as a baseline, we would see variability of people being higher or lower than what they usually do. But what that usual level is also is going to vary across people. Some people, if you ask them, will report more stress than other people on average all the time. So even though you ask them every occasion, you're capturing both cross-sectional mean differences as well as within-person fluctuation over time. Both of those things. And we can figure out how much we have of each with an intraclass correlation for the predictor. So just like we did for time-varying age, age is a time-varying predictor. That's the connection to this. So if we have a predictor that has an intraclass correlation of less than 1, then it has some kind of within-person variation to it. So it could have a within-person slope in predicting some other outcome. Having more stress than usual could correspond to more sickness than usual, or more grumpiness than usual, or something else on the Y side. If we have an intraclass correlation greater than 0, then it has at least some between-person variation, and that between-person variation could have a separate effect. The extent to which you are a high-stress person could correspond to average more of sickness, negative mood, whatever your outcome is in this case.
Lisa,
Yes.
aren't ICCs always greater than 0 or less than 1?
Nope.
No, okay.
If you have a data set that you don't know what the variables mean, and you get an interclass correlation for one of your columns of 1, what does that tell you?
That's all between.
That's all between. We call that a time invariant predictor. When would you have an interclass correlation of 0?
If there's no between person variation.
There's no between. So for instance, if you have balanced time, where it's not an accelerated design, everybody shows up at time 0, then time 1, time 2, then there's no between differences in time. That's what was last semester, because I took pity on you. Remember that part? So if you have balanced time that doesn't have any between person variance, then the only type of relationship that time can have is a within person relationship. So those are the extremes. If it's all between, we call that a level 2 predictor. If it's all within, that's level 1. But very few cases are going to have all level 1. It's usually going to be some blend of both. The relationships between predictors and outcomes could be the same direction across levels or different. So if I have time-varying stress and health, I may feel worse than usual when I'm under more stress than usual. That's a within-person relationship. People with more stress than other people on average could have worse health on average than other people. Both of those things could be true at the same time. They don't have to be in the same direction, though. They could be in opposite directions. So if I look at the relationship between exercise and blood pressure, when I'm actually exercising, my blood pressure is higher than I am at rest. My body is working. But at the between person level, blood pressure is treated as an indicator of overall health. So people who tend to do more exercise tend to have lower blood pressure. That's the opposite pattern in terms of the relationship. It would be a positive relationship at level 1. Exercise leads to higher blood pressure, but a negative relationship at level 2. Lower blood pressure for people who exercise more. So I have found it to be the case, especially in longitudinal data, but also to some extent in cluster data, that these types of slopes are going to differ across levels. The one reason is more theoretical because they mean different things. The reasons why people have different blood pressure than other people is not the same type of reasons why my blood pressure might fluctuate throughout the day, or my stress levels might fluctuate across time. But the more obvious reason why these slopes are going to be on different values is because they're on different scales. Do you remember back in like single level regression when everything was nice and easy? Remember that? We miss those days sometimes. We could output something called a standardized regression slope if we wanted to, right? Standardize it against standard deviation of x and y to create a standardized coefficient. Remember that? Well, if I wanted to do that here, I would have to think about x and y as level specific. So if I had a level 2 relationship, then the y variance I would standardize it against is the random intercept variance. A level 1 relationship would be standardized against level 1 residual variance. So anything predicting y is only going to be on the same scale to the extent that those numbers are the same. Otherwise, if the amount of variability differs across levels, and it differs differentially across x and y, then the coefficients are not on the same scale. So for that reason, we shouldn't expect them to be the same number. Here is what not to do. If you learn nothing else from me in your lifetime, this is it. This is the slide I'm going to die, the hill I'm going to die on, the slide I'm going to die on. And I have this noted here, unequivocally, this is wrong. It is also super, super common. What I have done here is take my time-varying predictor, put it in my level 1 model. Maybe I subtracted a constant so that 0 means something, hopefully. And I'm like, what's the problem? I got gamma 1O, that's the effect of time-varying x on y. For every unit higher time-varying x, y goes up by this much. Cool. The reason this is not cool, though, is that this gamma 1O slope both has to describe how differences between people in X relate to differences in Y, and how having more X than usual relates to having more Y than usual. It is doing the work of the two variables that are implicitly contained inside that time varying effect. So the answer that you get back, I call this the smushed effect, because every time I teach this, I have to do like a gesture like this, like they're smushed together across the levels. Other people will call this a convergence effect, a completed effect, or a composite effect. It always starts with a C. The answer you get back is usually going to be weighted more towards what the level 1 effect would be, because there's more information at level 1. We have more occasions than we have people. So really, the problem with this is not in the level 1 model, it's the level 2 model. The level 2 model is not going to be specified correctly. Graphically, it would look something like this. So on the Y side here of this slide 6, we started out with all of the variability in Y in one pile, and if we have a fluctuation model where we're not talking about change, then we would split that variability into level 2 random intercept variance, which is between persons, level 1 residual variance, which is within persons, and the model figures out how much of the variability goes on each level. So I call these piles of variance. You could call these variance components. It's not a coincidence that they're circles, because these are also latent variables from that perspective. So on the X side, though, we haven't done that. We haven't partitioned anything. So the slope that comes out of X to Y is really, at the same time, the between person part of X predicting the random intercept, and the within person part of X predicting the residual. And we're saying that those slopes are the same number, because we're making one variable do the work of two. So this is not going to work. Yes?
So you're saying that's happening even if people like person mean center?
No, if the person means center, then then you've done this. This is slide 11. Person mean centering is the easiest way to fix the problem. You literally carve the two variables up into their between part and their within part, and you put them in the model. And because at this point, this is a person mean right here, across time, it only has level 2 variance. The slope that it has can only be the level 2 slope. This variable is the original X minus the person mean. You have removed all of the level 2 mean variation from it. It's only level 1. So then the only thing its slope could mean is the within person effect at level 1. So this is what I'm going to recommend if you're in this world. You carve your variables up ahead of time, and they can only mean one thing. And if you leave either of them out of the model, you're saying that that slope is 0. The same as if you left anything out of a model ever. So this is called person mean centering in a longitudinal context. In a cluster data context, it's cluster mean centering, group mean centering, centering within contexts. There's a whole bunch of words for it. Yes?
So just to be clear, like the first example wouldn't have been like a grand mean center or something like that. Okay.
The first example, if you only subtract a constant or leave it uncentered, it doesn't matter, because all of the information is still there from level 2, and that's the problem. Yep. So since we're running out of time here, I'll do one more little expansion on this, and then we'll let you go. Question, Nathan?
Yeah, can you have a discrete time varying
Yes.
variable? Okay.
Same. Yes, same exact thing. Doesn't
Okay.
matter if X is categorical or continuous. The problem is still there. If it's categorical, it's a little more painful. Right, Vladimir? He's wrestling with these. So does this picture strike you as asymmetric? Like, why do I have boxes for my variables on X and I have circles for Y? Does that seem arbitrary? Yeah, but when you put it this way, it is. Like, why am I manually carving up X into different parts, but I'm letting the model do it for Y? Well, the answer is because I'm using multi-level software where I can only predict one column. That is why. If I switch to multivariate software where I can predict multiple columns, then I'll be like, hey, N+, can you carve up X for me like you carved up Y? Cool, thanks, and it will. That's called latent centering, otherwise known as multi-level structural equation modeling, to let it carve up X instead of Y. But that is the big advantage in this context of moving to a multivariate model. Because what if X has individual change in it too? What if people improve differently over time on X? You can't do this. There's no way to get an X slope into a box that's a good idea. So this sets the stage for X having its own growth curve potentially, Y having its own growth curve potentially, and you could have directed arrows or covariances among the parts at each level. Right, Carl? That's what you're going to do. You hope so, yeah. So that my hope is with these projects that you'll get to see what everyone else is working on, which will inspire you to think of new things to do with your own data, or potentially start to collaborate with each other. I know there are several of you who are working together on things, and I think that's great. But the rest of this will have to wait till next week. So stay tuned for the exciting conclusion of time-varying predictors. But yeah, if I teach you nothing else, don't do this. Don't smush. All right. Anything else before we call it a day?
One more quick thing. We only need residual terms for the outcome. Like if we try to separate intercepts and slopes for a time varying predictor, there's no residualness about that.
No, you still have residual variance to the as
you
long
do?
as you have
Okay,
more
for
than two
those.
occasions. Yep. Yep, the
Okay.
residual variance would be like the level 1 predictor in that situation.
Okay.